Hello, everyone. I'm guiltygyoza, co-founder of Topology. I'm glad to be here today to propose a new kind of decentralized program that is different but complements smart contracts on the blockchain. So what we really care about at the end of the day is to build better work computers. And we think there are three properties that characterize a good work computer. One, it needs to operate on a credible neutral protocol stack, because if it doesn't, then it's a centralized operated computer that's rented to users, and that doesn't really, shouldn't be characterized as a work computer. The second property will be it needs to accommodate as many concurrent users as possible, because people should be able to interact with the same computer concurrently around the world. And the third property will be it needs to operate on an open world programming model, meaning that people can deploy and use programs, and when program crashes, it shouldn't crash the underlying system. So the programming model should be designed in a way that assumes open world assumptions. So we have blockchains, and blockchains basically operate a replicated state machine over visiting consensus, right? So we're all familiar with how Bitcoin works. Bitcoin relies on nodes voting with their CPU power on state transitions, and Ethereum relies on capital put at stake for voting. Blockchain as an execution environment is a single-threaded environment. It's a single-threaded environment to include and order transactions. And for use, take Ethereum, for example, it has stored procedures, and people can invoke these procedures, which may change the state of a blockchain. And these procedures can initiate cross-contract calls to interact with one another. Now, we have scaling problems, and we have been concerned about scaling problems throughout the industry. So one dominant approach or philosophy for scaling will be modularity, right? So we are familiar with the modular thesis, which basically is about operating many, many single threads on top of a shared mother thread or parent thread, and these application threads basically settle their traces on the state space or the memory space of the parent thread. Well, the problem with this approach would be lock, which is common to all blockchains, right? Because single-threaded execution basically requires people to lock each other out when transacting against the same thread. So we can look at Ethereum's block time, about 12 seconds, 99% of which is spent on consensus or reaching consensus. Now, another approach complementary to modularity would be verifiable computing. So that gives you the ZK rollups. Verifiable computing basically allows these application threads to deposit traces, but compressed mathematically by the ZK proof on the parent thread. And additionally, this sort of justifies that, okay, sequencers can now operate in a central way. Provers can also operate in a central way because math never lies, and so nothing wrong can be ever deposited to the parent thread. So that is the assumption. Well, the problem with that approach is that we then have a bottleneck in liveness. So although the upper threads cannot deposit bad things to the parent thread, the upper thread can lock people out or can censor certain users from other users. So it becomes a bottleneck in liveness and censorship. And also, it basically increases the complexity of the already very complicated protocol stack. And finally, for each application thread, we're still operating on a single thread. So the question will be, how can we break away from single thread? Well, we can basically look at the assumptions of all blockchain, which is they all operate on the strict serializability model, which means that operations do not overlap, and operations are put in a single total order. So that's the total ordering property. Bitcoin relies on CPU voting to decide on the ordering. Proof-of-stake blockchain requires basically voting by their stake to order the transactions. A weaker consistency model called causal consistency model is the model that we really care about, because causality is the upper bound of the kind of consistency guarantees you can get while you do not need any coordination. And coordination is voting, is consensus, is what really takes up the majority of the time for these distributed systems. So in short, if we stick to the causal consistency model, we can skip the voting and consensus entirely, but still guarantee that all replicas reach consistency at the end of the day. So the fundamental building blocks here will be a hash graph. A hash graph, we have to talk about the basics system model assumption first. So the basic model assumption is we have a distributed system of many, many processes, and every process is a single thread. And these processes will generate events. whatever kind of events that they might generate. And these processes communicate to one another via passing messages. And these message carries the information about the events. And they do these without locking each other out. So message passing is performed in an asynchronous manner. Now, for a hash graph, the message takes the structure of the event payload, followed by causal dependencies, followed by signature. So signature is just standard way of basically identifying who is sending the message. The causal dependencies is for a message to basically report what messages prior to me is the messages that I'm depending upon. So for example, if you look at this hash graph, the message C2 on the very right has the dependency of A2 and B2 because these two messages precede C2 and is the dependencies reported by message C2. And we further require that when you generate an event locally, you need to report your dependencies as the heads of your graph, which is the most recent nodes in your graph. So if we have hash graphs, we can start merging them. So imagine a system of many, many processes all doing events asynchronously, and so they have different hash graph. Now, if we have divergent hash graph, that's not very interesting because everyone is he says, she says. But if we can merge these graphs into consistent graphs, then now we have synchronization, and synchronization is good. So if you look at these two graphs on the left, they can merge into the third graph on the right, where all the causality relations are still preserved. So that means that you can merge these hash graphs that all originate from the same state, original state, and you can merge them whichever way, and they will give you the consistent graph that still preserves the causality relation. And the way to merge graph or to basically transmit information across the network would be you have the pole model, which is that these replicas basically perform anti-entropy among themselves and they reconcile their graphs. And there's the push model, which means that these processes sort of gossip messages over the P2P network. Okay, so why do we care about hash graph? Because there's a property called invariant confluence. Invariant confluence is a property about distributed system that says if a program is invariant confluent, the program can be executed in a distributed manner without relying on any coordination. And if we look at the hash graph, we can see that if you can merge hash graph arbitrarily and still get a valid hash graph, then hash graph itself is an invariant confluent program. And so what this basically means is that we can run a distributed system that basically communicate and synchronize on their hash graphs, and there's no consensus mechanism or any voting required. But everyone is still able to operate correctly. And the property for Byzantine faults will be this has the property of being Sybil immune. And so if you look at blockchain, there's basically assumptions about majority, right? So Bitcoin traditionally assumes 50% majority, to be honest. And Ethereum basically relies on 66% of stake being honest to be able to progress and to be not basically revert on their finality. And if you have 33% of the Ethereum node corrupted, then the blockchain can be stalled. But for this kind of operation, you will be immune to Sybil faults, which means that even if your network is 99% Sybil, as long as the rest of the correct nodes are still connected in a continuous graph, then the correct nodes can still operate correctly, regardless of how many Sybil nodes are present in the network. So with all these properties, as programmers, how should we leverage these properties? So there is a data type called CRDT, or conflict-free replicated data type, which is a data type that basically abstracts all of the properties above. And it basically gives you the common API that programmers are familiar with. APIs like the register API or the set object, array object, or map object. Furthermore, these objects can be composed among one another. So that basically gives you JSON or recursive maps. So these CRDTs are composable and they allow programmers to express arbitrarily complex behaviors. Furthermore, we can have BFT CRDT, which means that you can have these replicated data types that are concurrently operated upon by many, many replicas, and they can be immune to Sybil actors in the system. And so on the below, you have a very basic CRDT called 2P set or two-phase set. A two-phase set is a mathematical set that allows you to add elements to the set and then allows you to remove element from the set. But once the element is added, it cannot be removed. Once an element is removed, it cannot be re-added. Therefore, it's a two-phase set. And you can see that from the left, you have an empty two-phase set. And in the middle, we have a hash graph that transport a bunch of operations that are being performed on a two-phase set, where the the A events are the add operations, and the R events are the remove operations. So following this graph, you will have a new two-phase set on the right, which has element 2 and element 9 remain in the set. Right, so the summary for here will be, we have these wonderful properties about I-confluence and about having a distributed system without any consensus mechanism required and so on. And then we can abstract all these as a abstract data type for programmers to create programs, and that is the BFT CRDT. So we want to propose a new kind of decentralized program called live object. For blockchain, you will have smart contracts. For this new paradigm, you will have live object. So live object is an object, so it's following your common object-oriented programming. Objects are stateful, and they expose methods for manipulate their own states. And we call them live because these objects will have very low response time because they operate locally as local replicas. That allows you to transact against the local replica instantly, and basically you can read after your read, and you can write after your write and write after your read instantly. These are actors, furthermore. So this is the actor model where different live objects that are, each one of them is a BFT CRDT. They can communicate via asynchronously passing messages to one another. Just for some terminology, so live objects basically is an instance of a blueprint, which is a class, and these classes are composable, so you can have class compositions. Every blueprint will have states, and states are typed by CRDTs or maybe typed by other blueprints, so you can compose blueprints. Every blueprint will have an interface that specifies the set of signals that this particular object responds to. It will have, obviously, handlers or functions that handle signals when they're received. And it will furthermore have, a view function, a materialized view function, basically allowing you to query the state of the object. And it will have a merge function that specifies, if I have two replicas of the same object, how do I merge them together? The affordances of live object relative to smart contract will be, one, it is default free because there's no consensus mechanism required. So transacting against live object does not require paying transaction fee to pay for consensus, whether that's paying for CPU power or whether it's paying for, in terms of proof of stake, you're basically paying for the yield that is expected by the capital at stake in the system. So it's basically free transactions, and furthermore, it runs at local speed. So imagine every replica running at 60 hertz locally. So that's 60 frames per second, which is commonly what video games run on. The system will be horizontally scaling, which means that for every new user added to the system, they can transact at 60 hertz without slowing everyone down. And the third property will be they are loosely coupling, meaning that these objects do not interact by function calls. They interact by passing messages, so they do not lock each other out. Furthermore, this will be discussed later. Each object can be synchronized on the individual basis, right? So if you operate a full node for Ethereum, you basically have to synchronize the entire state, which contains the universe of all smart contracts. Even for a lot of smart contracts, you actually do not care about. But for live objects, you can basically subscribe in terms of a public subscribe pattern to a particular object, and you will only synchronize up to that object, which allows you to not care about other objects and to be able to run a node locally. So this is the pseudocode for a social graph. So we are probably all familiar with Farcaster. What we may be less familiar with is how the Farcaster hub network actually works. The hub network of a Farcaster actually operates a set of CRDTs. So the Farcaster social graph is composed of roughly 8 CRDTs that basically record people adding posts and remove posts, people reacting to posts, and people following other people. So a social graph can be represented as a live object. As a result, you can make social network as live objects. Another example will be a multiplayer simulation. So all video games or all metaverse-like applications basically is in multiplayer simulation. You can have a multiplayer simulation structure as a live object, and the question here will be, how can we do collision? Because if you are in a virtual world where nothing collides with each other, it's not really interesting, right? Collision can be achieved by basically endowing each rigid body with a field. And when these rigid bodies collide, or when you're merging these replicas, you will reconcile these overlaps of the field, and you will basically push the rigid bodies apart from one another. So this is a proof of concept we did last year, where we have about 10 different users, each operating from their own browser, and this is purely peer-to-peer, synchronized between browsers by representing the underlying world in a CRDT. And as you can see, these penguins do not overlap, so that's not very interesting. So the next proof of concept will be actually implementing collision. So a penguin is operating from Taipei, while the other penguin is operating from somewhere in the United States. And as you can see, these two rigid bodies actually collide. And these sort of rules are all encoded in a CRDT. So now we're ready to introduce the RAM concept. RAM, or random access memory, we find it as a very interesting analogy for 3 reasons. So random access basically means that I can access particular data from the memory space, right, at constant speed. So for live object, you can subscribe to particular live objects in disregarding other objects. In contrary, for blockchain, you have to synchronize up to the entire state machine. Another property will be caching. So because these replicas operate locally, is very close to compute. So that basically mirrors the idea of a RAM being very close to CPU and have fast access time for CPU. And the third property will be ephemerality. So we imagine these live objects, when no one is using it, it will basically exist as a snapshot on IPFS. And when someone wants to use it, the snapshot will be rehydrated and becomes operating as a replica and synchronizing among replica. So an object can be in active form, and it can also be in dormant form when it exists only in a snapshot. So we can talk about interaction, because if these objects do not interact with one another, there's no interoperability. We can have interaction by passing messages, but in order for these message passing to be trust minimized, the receiver object basically needs to verify the incoming message and the causal dependencies of the incoming message. So if you look at this diagram, we have 3 objects, X, Y, Z, and the message X9 basically initiates a signal that creates a message Y5 in the second object. And so the Y5's causal dependency has both its own dependency in object Y and also the dependency of the sender object's dependency, X8. And the same applies for Y7 signaling to Z and generating Z5 message. You will have dependencies on both your own object and also the sender object. So we have talked about the basics of live objects and how they interact. Now we're ready to talk about some intuitions behind how we may construct a protocol stack. So we have to start with global snapshots. Global snapshots are basically, we can talk about why. So for example, if you play games, you will want to periodically save your game. So saving a game is a snapshot of the state. Second, for these asynchronous objects to sort of gear shift and transact with the blockchain, you have to take a snapshot of it. And then you will commit transactions on the blockchain, because transactions on the blockchain are irreversible. So you have to, for these different replicas, you have to find a common ground, and then you interact with the blockchain. And third is, if you want to compact these graphs, you have to first take a snapshot and then decide what part of the graph you can prune away. And pruning is very important, because for a blockchain that may grow over years, these live objects, with people transacting with them at very high speed, the graph can go very fast. And so if we don't prune the graph, this is basically impractical. If you want to do compaction or pruning, you have to take a snapshot first. So snapshot is important. For objects that may have been permissioned, or for objects which has basically leader nodes that are asymmetric from other nodes, the leader nodes, the trusted nodes, can perform the basic global snapshot algorithm, such as the Chaney-Lamport algorithm. But if we are moving towards open access live objects, where these replicas are all on an equal basis, then the problem, it becomes a problem, because, okay, we can say a global snapshot is the merging of all the replicas of the object, but the notion of all is very problematic, because on the open peer-to-peer network, people can join and leave. And so gather information from everyone can be very impractical. And also, as you're merging these replicas, what is good and what is bad, and who to decide what is good and bad. So basically, this means that we need to introduce consensus. Consensus means that we need to agree on, given all these replicas of the same object, which replicas are to go into a snapshot. Okay, so we can talk about compaction a little bit. Compaction basically means pruning the graph. So on the left, you have a large graph. If we assume that message F and G in the middle are stable, meaning that no future events will have come before F and G, then we can prune away the messages before F and G, basically saving space. Otherwise, this graph grows indefinitely, and you will have a memory-bound problem. So The topology protocol stack can be understood as a layered architecture. From the bottom, you will have P2P messaging. On top, you will have a hash graph that gives you causal consistency. And then on top, you can have a threshold witness, which is basically the threshold logical clock that will basically allow you to say, okay, I am assuming that this information is known by everyone, or at least known by 2/3 of everyone, and that 2/3 of everyone acknowledges that they know the information. So then you can basically operate a synchronous clock, on top of which you can operate consensus. And consensus may be important if we want to operate a proof of stake mechanism. Since time is up, I'll be quick on the last few slides, and there's a paper at the end, so for those of you that are interested, you can read the paper at your own pace. So we can do a threshold merge hash graph, which means that, okay, if we cannot say, let's gather all the hash graphs, we can say, let's gather 2/3 of the hash graph, and because we don't want to be Sybil attacked, we can say the 2/3 requires to be the 2/3 of the stake, protocol stake in the network. Once you get all these hash graphs, you merge them together, that is your global snapshot, and you can compact away the snapshot. So compaction works like you would get agreed upon snapshot of the graph, and you would compact it away by basically transitioning the state with the graph of the messages. And in order for these graphs to be succinct and also trust minimized, similar to how the Mina blockchain works, we can say, okay, whenever you're transitioning the state, you're also performing a validity proof or recursive snark or recursive stark over the state transition. And you will keep that proof in your graph, so that people can basically fast sync on your object without having to traverse all the way from the beginning. The status of the project will be, we are currently on paper draft version 7.3. This is a QR code that will bring you to the paper draft PDF. On the engineering side, we're doing a vertical prototyping. We hope that by summer this year, we can give people non-BFT version of live objects and people can play with it. On the research side, there's a lot of open problems that need to be figured out, and we're setting up an office in Berlin. Some open problems include that we need to figure out a consensus protocol that minimizes the complexity of communication over the network, that keeps these objects succinct, otherwise they grow very fast, that have a suitable proof of stake mechanism, and so on. And there's problems with crypto economics that need to be figured out. There's problem with the underlying broadcast algorithm because it affects how efficient information transfer over the P2P network, and it affects how fast these objects can synchronize information. And so on. And we're looking for engineers and researchers who have experience in Go Rust programming, P2P networking, distributed system, cryptography, and crypto economics. If interested, feel free to contact me on email or on Twitter or on Farcaster. Thank you.
And now we have 5 minutes Q&A time. Does anybody have questions?
Hi, hello. I've seen a similar using hash graph systems like Hedera or some DAG systems like IOTA, Phantom. So how is the RAM protocol different from those already existing graph-based systems? Thank you.
Yeah, so there are many DAG-based blockchains being proposed, and we have the Sui and Aptos, which operate on sort of the Tusk consensus mechanism and the Borchardt consensus mechanism. I think the difference between CRDTs and them is that they still operate Turing-complete smart contracts. And for Turing-complete smart contracts, the transaction ordering really matters. Like who writes to a particular state variable, who gets there first really matters. But for CRDT, we're basically saying, okay, let's not do Turing-complete. Let's do a subset of the possible programs that can operate without having to order things. And so by doing this, we can skip the ordering part. So if you look into the Borchardt consensus mechanism, you'll find that they basically have to total order the blocks in a DAG. And total ordering is needed because they're operating on the Turing-complete model.
Any more questions? Any more questions? Okay, then thank you, guiltygyoza, for the talk.